There was a slight notational error here. It's B times D, not B times C. So at the end there, it should be B times D, not B times C. It's often said that vector spaces are defined over a field. This is because vector spaces often use the addition operator from the field to define their vector addition operator. Additionally, scalar multiplication is defined using the multiplication operator from the field. Now, in your homework assignment, you're going to be practicing using multiplication operators that aren't your standard multiplication operator. But in using them, you'll prove, hey, we do form a vector space, which is kind of cool. So in many cases, we classify vector spaces by the field over which they're defined. So a complex vector space complex vector spaces is an example of this. So a complex vector space, or C vector space, is a vector space where the field is the complex that adds better numbers. Okay. And a real vector spaces a real vector space, or R vector space, is a vector space where the field is the real numbers. And being told that the field is the real numbers, when we're told that the field is the real numbers, we can assume that it's the standard multiplication and addition operators. And same if we're told that it's the complex vector space, we can assume that the addition operator from the field is the standard addition operator, same with the multiplication operator. And this leads to probably the most well-known vector space. And when you think about vectors, probably the thing you're looking at. And it's the real n-tuple vector space. Now, we have an analogy for the Cn vector is the set of x1 through to xn, where xi is an element of the complex numbers. That would be the complex n-tuple. But in the real n-tuple, adding two vectors, this is how we define the addition of the vectors. And it's defined using the standard addition from the field. So here, this is our vector addition. And this is our field addition. And here, same thing with scalar multiplication. This is scalar multiplication. And this here is our field multiplication. Now, given this definition for addition and scalar multiplication, we can prove it's a vector space. What does that mean? We can prove it satisfies those conditions of being a vector space. And proving these axioms of a vector space is a good exercise, but takes some time. So I encourage you, prove it for yourself. Prove that it does in fact form a vector space. And we're going to prove that together. And we're going to prove one of these pieces together here. We're going to use a technique called a direct proof. And for those of you who aren't familiar with proof techniques, we're going to be going over some proof techniques throughout the course. A direct proof is proving the statement is true or false using established definitions. Axioms, lemmas, or theorems, without making any further assumptions. So what this means is, based on what we're given, we're able to prove what we want to prove. So if, for example, if we do A1, we want to prove that x plus y plus z equals x plus y plus z, and then we put brackets here and brackets here, because we are proving associative. Okay, so we want to prove associative. So here I'm going to start with x1 xn plus y1 yn plus z1 to zn, and I have brackets here. And now this gives us brackets x1 plus y1, comma, x2 plus y2, comma, xn plus yn, all plus z1 up to zn. And here, and we're going to do the right side argument shortly, this here is by the definition of vector addition. Okay? And now from here to here, I'm going to use the definition of vector addition again. But I get x plus y all plus z1, because it's this whole thing as a group. We're now treating this here as if it's a single group. Whatever that is, stays as a group. And we're adding z1 to that group. So we get x2 plus y2 plus z2, xn plus yn, all plus zn. But now inside here, and once again, this is by the definition of vector addition. But now, here, we're in a field. So we can swap the order of these additions, each individually, by the as addition, as scalar addition or field addition is commutative. So this equals x1 plus y1 plus z1, x2 plus y2 plus z2, xn plus yn plus zn as field addition is associative. Remember, we're assuming we're in Rn, so you could use the fact that real numbers are standard addition for reals are associative, but this addition comes from the field, so and because of that, it's associative. So for this example, it probably more exact. Instead of saying as field addition is associative, we would say as the standard addition is associative over 4 real numbers. And now here, this we get x1 xn plus y1 plus z1 up to yn plus zn, which is equal to x1 to xn plus bracket y1 to yn plus z1 to zn, which equals x plus y plus z. And now we've proven it's associative. Now you can go all the way from left side all the way to right side, or you could get about here, and then you could do this as your right side and work your way down and get to here, and then link these two using the associativity of the field. And proving these different vector spaces we have are vector spaces. Typically, that's what it's going to go down to, is it's getting to a point where using the field axiom, we can prove the space is in fact a vector space. Okay, I encourage you to go through the other examples on your own. Lastly, what we're going to do is we're going to look at calculating some vector addition using these n-tuples. So here what we have is we have x equals this expression. So we're going to start by calculating x. X equals 1, 2, 3 plus 2 times 1, 1, 1 minus 3, 2, 1. Just apply your brackets in your rules. So it's 1, 2, 3 plus 2 times, this is subtraction within it. So it's 1 minus 3, 1 minus 2, 1 minus 1 equals 1, 2, 3 plus 2 times -2, -1, 0, which equals 1, 2, 3 plus -4, -2, 0, which equals -3, 0, 3. And we are done. I will leave y as an exercise. The set of vectors 1, 0, 0, 0, 0, 1, or 0, 1, 0, and 0, 0, 1 are nice because every vector in R3 has a nice representation. X, Y, Z equals X 1, 0, 0 plus Y 0, 1, 0 plus Z 0, 0, 1.